When we go through and look at these, all the Diels-Alder reactions, pretty much everything that you can expect to see on either an exam or potentially even in the future, if you were going to take any more organic chemistry. As soon as you think you've got a Diels-Alder reaction, just draw the cyclohexene. Yes, there are hetero Diels-Alder reactions, but you won't see those as often. The textbook mentions them, and I think there's one homework question on it, and that's it. Okay? So at very least, we know that's going on with it. One thing that can make this complicated is that you may have noticed that I drew all these cyclohexenes in the exact same fashion. Okay? Where the left side of the cyclohexene came from the diene, and the right side came from the dienophile. Okay? Very simple fix to mess with everybody drawing or trying to solve a problem. Let's say if we tweak this. It's amazing. Well, it's not that amazing because Diels-Alder is just a pain. Oh, shoot. We do that plus this. And now everybody freaks out, has no idea what to do. Okay? Sigma bond rotation, and it's a little bit worse than that. Not only is it just sigma bond rotation, I just changed the orientation of the two, okay, in space. The Diels-Alder requires so much spatial awareness that any slight permutation off of just the standard, the left is the diene and the right is the dienophile, and I make the cyclohexene, throws a monkey wrench so massive into being able to come up with an answer that most students will get the question wrong just by simply changing the location. Okay? So you are probably one of those students, and I don't mean that to be offensive. You just probably are. So if you see it drawn out of normal alignment, what should you do? Redraw it in the normal alignment so that you can get to your answer. Okay? That will make it amazingly easier to go through and solve just by that simple adjustment. The next part is that you do form a cyclohexene all the way through it. Okay, so set up your cyclohexene all the way through. After that, start putting in the groups that are missing. So in that first one, that should be an NH2, so we'll go ahead and draw that as an NH2. And actually I'm going to skip that one, I'll come back to it in a moment. The next one, we've got a methyl up there, and the last one I have a methyl and a methyl. And then I also noticed that I've got my carbonyls coming off the side. At this point is a very good point to check your multiple choice answers. Because at this point you may have eliminated it and you have your answer and you can move on. More than likely you won't have eliminated your answers. In fact, just to make sure we don't get too excited, let's just ignore that one for the moment. More than likely, what is going to be wrong? Why are these not going to be shown in your multiple choice answer? Both of these have stereochemistry associated with them. That stereochemistry has to do with the spatial arrangement of those groups during the mechanistic reaction. Okay? In most cases, or most other reactions, you can draw out a mechanism and you can start to at least pretend to get a feel for the spatial arrangement. You draw out the mechanism for a Diels-Alder reaction. Whoops, that's an eraser. And that gives you absolutely no information about your stereochemistry. Okay? So you have to have a much better understanding of how these molecules are reacting in three-dimensional space. Okay? Those people watching the video at home will have a hard time catching on to this, but let's take a look. Let's make sure I line this up right. Right hand, I have the diene. Does that look like the diene? If I line that up, is that on your, that's the right side of your screen, isn't it? Okay, there's the diene. My thumb is a double bond, my index fingers are the other double bond. Okay, there's my diene. Where's my dienophile? There's my dienophile. Now my left hand. Okay, what I'm doing to do the Diels-Alder reaction is that those then overlay. The new sigma bond is forming in that kind of diagonal gap between my right hand and my left hand. that is the new bond. Those are the new sigma bonds. Okay. Where does this become relevant? Well, this is now going to have to do with stereochemistry. Okay. The other issue that we got to watch out for is, yes, I could overlay in this fashion, or is that going to change the orientation of everything?
Yes.
Yes, but it will change it consistently. Everything changes. Okay? So, if we take a look at that top right one, I need to go through and show a methyl on my diene. How can I show the methyl? Where is the methyl? Index finger or thumb? Good, it better be my index finger. I can't do it otherwise. Okay? At that carbon, there are actually two things attached to it beyond the double bond. What are those two things? Hydrogen and methyl. I now have my hydrogen and my methyl. Where's the methyl? The silver part of my pencil, and the hydrogen is the bottom one. So now what I do is go back to my reaction. I, for some reason, always put the diene on top. I don't know why, but that's what I do. Okay? Here's my dienophile coming in to form the bond. Where's the new sigma bond form? Okay, below and in that kind of diagonal space. That means the carbon where I'm holding that pen is now switching from being sp2 hybridized to sp3. It is no longer planar. It must shift out of the plane. There are two ways it can shift out of the plane. That's one way, or that way. Both of those options are now going to change where the methyl is. If it rotates this direction, the methyl is now up. If it rotates the other way, the methyl is down. So we might say, oh, there's two products that we have to then watch out for. Okay, is there? For it to rotate down, what is that inner part of my pen rotating through? The bond that just formed. Can I move an atom through a bond? No. So what happens? That inner bond moves upwards, which means my methyl is necessarily aimed down. Clear as mud. It involves lots of spatial awareness on what's happening within that. Okay? It involves so much that my arms are now getting tired of holding my hands up and showing these kind of things with my hands. I would recommend a model kit to kind of help out with this. That will help to a certain extent with the spatial awareness. Just realize that if you use pi bonds with your model kits, what happens to the bond rotation? There is none. You have to kind of imagine a rotation happening with it. Okay? So, with our stereochemistry on that one position, we said the methyl went down. What happened with the diene? Okay. There's now one of the carbonyls. I don't have another finger to use. Actually, there we go. No, that didn't work. There's one of my carbonyls. So if I have that new sigma bond or that new orientation stack in this fashion, okay, the new sigma bond forms in that angle, which means where does my thumb need to rotate? It must rotate away from that angle, which then means my thumb is down. Okay. And in all of these reactions, you'll notice that I'm always showing that group aiming towards the diene, which you may go, well, that's a really odd, awkward orientation to show it because it gets in the way. That's true, it does get in the way. But the other orientation is like that, right? Where my thumb is now aimed the other direction. What happens when we go through to make that bond? Now where's my thumb rotate? It rotates up. Okay? So we get a slightly different orientation or a different product by changing the orientation of the dienophile. Okay? Which means, again, more products. However, based on running the experiment multiple times over, what we have found is only one orientation works for the dienophile. That orientation is where that extra group is aimed at the diene. Always. That attack is known as the endo attack, whereas the other orientation is the exo. The endo is the only one we have to worry about. Okay. The explanations for why are in the video, which hopefully you all watched, and you can get some kind of idea of what's happening within those. Which means when we now go back to the structure, or our answer, those groups must be aimed away. If that was the only answer you wrote, technically you're wrong. What's the other product?
The enantiomer.
Plus the enantiomer. Okay. What about the bottom one? Well, if we assume the same orientations, we can go ahead and just automatically draw those both as dashed. How could I get one wedged and one dashed? In here, how could I get one wedged, one dashed?
If you have transformation.
If I have the trans dienophile. We now run to the issue with the stereocenters for the other two methyls. Should they be on the same side, opposite sides?
The one down is the same side, the one up is opposite.
They end up coming in on opposite sides. Okay, how do we know that? You just saw me wave my hands around and point pens and all that fun stuff. You're doing the exact same reasoning behind it. Which way does that bond, does that carbon atom, my thumb or my index finger, have to rotate, okay, if we have that bottom attack? Anything on the inside of my hand must rotate one direction and one direction only, which is up. So anything on the inside portion of my diene must be aimed upwards. Anything on the outside portion must be aimed downwards. Okay? If this was your final answer, you would still be wrong because you still have the enantiomer. The last one, okay, there are two possible ways that this reaction could occur. I could have the double bond drawn as it is shown, or the diene drawn as it is shown, or I could draw it where it came in from that orientation. Okay, just changed it around. What we have is now two people coming together, okay, and they're in space, free floating. We tell them to form a circle. They can form a circle in two ways. They can take their head, attach it to the other person's feet, and head to feet, or we can do head to head, feet to feet. Yes? Okay. We now tell them they have to make out with whatever end they're touching. Is there a preferred way that those people are going to orient? Assuming we remove any sexual preferences or fetishes. Okay? Theoretically, you're going to get head to head, foot to foot. Okay? Because you don't want to be making out with somebody else's foot. Okay? Same kind of thing is happening here. What determines the head? What determines the foot? The organic chemist's four-letter word. What charge builds on this carbon? Negative. Whoops. What charge builds on this carbon? Positive. Which two carbons should be next to each other in our Diels-ALder reaction? We can't exactly draw that cross, so if we were going to attempt to draw out our product, we still have our cyclohexene. Would go through and draw on my NH2, and now I've got to be careful on where I draw that carbonyl. Where should the carbonyl show up? We will call it blue carbon or purple carbon. The carbon where my nitrogen is connected to the carbon closest to the carbonyl, which means there's my carbonyl. Okay. Do we have stereochemistry to worry about? Yeah, we still got stereochemistry to worry about. Which I didn't think about when I tried to come up with the answers. Dagnabbit. So we do the bottom there and plus the enantiomer. Okay. No judgments. Who watched both Diels-ALder videos, or who didn't watch both Diels-ALder videos? Okay, fair enough. Just realize that's where you're going to find most of that information. Okay.
So if we drew both for the first example, is it wrong?
What do you mean by
And then
both?
One is preferred where the carbonyl is attached to the purple ones. So both the one is that's attached to the blue.
Those
one,
two?
Yeah,
Yeah, the black one's wrong.
it's never formed.
Not formed in any amount that is considerable for an answer. Never formed is a bad word in organic chemistry. It can always be formed. Is it formed in an amount that would even be remotely considered a product? No. Okay? Don't look so depressed. That was the hardest part. As I dropped stuff. Yes?
I'm trying to figure out on that one, on the second one, I think it should be like if.
That second one?
Yeah,
Okay.
if the methyl should be up, I think the dienophile should be down.
They're all on the same side. So, if we take a look at it again. That structure matches as I got it up there, right? And this goes in to do the attack. This guy must rotate down. This hydrogen must rotate up, which means the methyl is now down. Everything's down. Or if we do the opposite orientation, where we come in from this angle, okay, this rotates up. That hydrogen would have to rotate down away from the ring, which puts the methyl also up. They're all on the same side.
It's because of the orientation of the dienophile, it has to be like.
If we look at the orientation of the dienophile, this always holds true. We always have the endo. That would be the orientation of the dienophile the other direction. That's the endo, or the exo product. We don't get the exo. It's always the endo. Okay. If you have questions about it, feel free to ask after class. We'll play around with model kits. It's helpful. Okay.
Another orientation where instead of coming in this way, it's like a lateral.
No lateral, and the reason why no lateral. The mechanism is concerted. All the sigma bonds are formed at the exact same instant. You can't come in lateral because then you wouldn't be in a proper distance to form that second sigma bond.
So if it is coming lateral, it's really kind of reaction.
You wouldn't see a Diels-ALder reaction. Right? If you saw any reaction, it just wouldn't be Diels-ALder. Okay. When we talked about permanganate, so the other section of chapter 24, we've got osmium tetroxide, potassium permanganate with two conditions, and ozone. Those are your four major reagents on top of Diels-ALder chemistry in chapter 24. There is the periodate ion, which is also involved. We're just not going to talk about it in lecture. It's ultimately doing the exact same thing as everything else is. Okay. In all three of those cases, you are forming, or 4 or 5 of those cases, you are forming a 5-membered ring, okay, as a transition. The mechanistic detail behind that 5-membered ring isn't super relevant. What you are responsible for is knowing what the product is. So we will look at some of the mechanistic detail, but only to a certain extent. Okay, so when we were under concentrated hot conditions, we now increase the likelihood of permanganate interacting with the alkene, which gets us our 5-membered ring. Because we are now concentrated, it does not fall apart as easily, and it's now kind of frozen in that place until it has enough energy to do some reaction. Okay, well, if it's cold, the fall apart mechanism happens relatively quickly, and we just do the diol. With it being hot, we've now increased enough energy that we can start to break other bonds. Those other bonds of being most important would be the carbon-carbon bond. Why do we need heat to break that carbon-carbon bond? Why is it more stable?
It's carbon.
Yeah. Why does that make it more
Yeah,
stable?
same one.
Same electronegativity. There is no displacement of those electrons, so it's going to require more energy to cause that to break. So we can cause those electrons to shift outwards towards that oxygen. What happens to the oxygen now? It has too many electrons, so we have to kick electrons out, which can go to the permanganate. The permanganate, or the manganate ion, now has too many electrons, so it can kick electrons out as well. The net result is that we now have, in this case, a dialdehyde, okay, or a dicarbonyl. Right? So the way that we talked about the shortcut on this is if you see your alkene, redraw it where you've now stretched that alkene bond, erase the middle of it, and put in oxygens. Okay. The next part of this is realizing that we are doing an oxidation reaction. Okay. Permanganate can't stop oxidizing. It just oxidizes the crap out of whatever it touches. And when we looked at our oxidation reactions, it's increasing the number of oxygen bonds, and it is also decreasing the number of hydrogens. So when we look at this intermediate still has hydrogens connected to those carbons. So the permanganate will continue to react and end up putting in oxygens or trading oxygens for those two positions. Right? Those would technically be negatively charged. We can follow this reaction up with a little bit of an acid workup. That acid workup protonates those, and we end up with the dicarboxylic acid. How is it usually buried? 1, 2, 3, 4. You will almost always see it stretched out, as opposed to having it circled back in on itself. Okay? You can use whatever reasoning you want to for why they've stretched it out as opposed to circling it. Personally, I'm a pessimist. I think we stretch it out so we hide that information, so you have to know what you're talking about as opposed to just saying it looks close. Okay? Questions? The new functional group, which we will talk about in depth later in the semester, is involved in this next step, which we already just kind of skipped through, is that as long as you have hydroxide and a carbonyl, that hydroxide can react. See, did I actually show it nicely? No, I didn't show it nicely. Our carbonyl has a resonance structure where we put charges on the oxygen and the carbon. So in the presence of hydroxide, what can happen? Well, the negatively charged hydroxide can react with the positively charged carbon. This is an interesting chemistry from carbonyls, which we will see towards the end, or actually, I think in the next sequence. Okay. That then forms the diol state, which we got previously when we react with just our permanganate to begin with. Our manganate can react with that. It can then go through a very similar series of mechanistic steps that ends us at the acid. As long as we have an oxidizable carbon, meaning we have a carbon with hydrogen that has already been polarized by another oxygen, we will keep oxidizing that. So it will continue down to the acid. So that when we looked at the example over here, that final product is the one with the diacid. If we look at the other reaction, we can go through and drop in our oxygen. So we pretty much erased and did that just cleaving of the alkene and dropped in the oxygens. And we now have to evaluate the carbons that are involved. Do those carbons still have hydrogens attached to them? One does, which means oxidize it again, put another oxygen on it. The other one does not have that hydrogen, so leave it alone. We can't do anything else to it. Right? That next problem we looked at, okay, we could do the same thing with that one. We stretch out that double bond in between. Okay, we don't touch the aromatic ring because it is aromatic. It is super stable. Okay? Because it is now super stable, it cannot react. And we're left with those two products. Before we say we're done, we look at our carbons and say, do we have hydrogens left over? Yep, which means continue to oxidize. And we'd end up with our final product of our benzoic acid, I know that looks like an A, and CO2. Last one, the real big addition there is that triple bond. You're doing the same thing you've been doing in all the others. Okay? You go through, you cleave that open and evaluate what happens. Okay? We'd have to have a triple bond to an oxygen. Right? Can I have a triple bond to an oxygen easily? No, so what happens? I need a third oxygen. Okay, our carbon is unsatisfied on the last one. We get the double bond. Whoops, it still had a hydrogen. Sorry, I don't know why I didn't think of that. Still has that hydrogen, so it can be oxidized one step further to forming our CO2. That rest of the ring structure, what happens with the ring structure? Are those alkenes or aromatics? Alkenes, which means we've got to oxidize those out to our acids. Questions? So, ozone is kind of notorious. They'll give you a structure with a whole bunch of alkenes in it and then ask what the product is. Right? Most people will see one product. Very likely if you're doing an ozone reactor, sorry, not ozone yet, permanganate with an alkene structure, you're going to be getting multiple products. Okay? Questions? Yes?
So you just keep oxidizing as long as there's a hydrogen?
As long as there's a hydrogen attached to that carbon, you oxidize the crap out of it. The carbon where your chemistry started, where did your chemistry start? The alkene carbons and the alkyne carbon. Okay, because it's reacting with the pi bond. So you just keep oxidizing until you've gotten rid of all your hydrogens and you've replaced them with oxygen bonds. What's the face? You're good?
And did you say again that the O2 double bond, or the oxygen with carbon double bond switches to OH?
So let's stepwise that. So what we would go through and do is, oh, that looked horrible. Let's try that again. There's our stretch double bond. We erase the middle of it out. Put in our oxygens. Before we decide that this is our product, we now have to evaluate the carbons that I highlighted in blue and look at those carbons. Can those be oxidized further? Well, what else is attached to them? Hydrogen. Can I remove hydrogen in a redox reaction? Yup. So as soon as I see that hydrogen, I can now erase it and turn it into OH. That's when you decide on that last oxidative step.
No, I'm talking about the double bond oxygen. Like when you form the resonance structure to have the negative oxygen.
What you're talking about there is getting into the mechanistic detail. I don't know why you're going into the mechanistic detail. Okay, no, that's fine. That ultimately has nothing to do with predicting the product.
Okay.
All that has to do with is when we run that reaction, our very first part stops here at, say, an aldehyde. that aldehyde reacts with hydroxide. To form the diol. That diol reacts with permanganate that says Mn. This is now your active species that does the oxidation. Okay? And if we have a hydrogen there, that hydrogen can be removed by a base forming an alkene, electrons, or sorry, not an alkene, a carbonyl, and then these electrons come back down. Okay? This step we'll talk about a lot. Okay? That step is super, super relevant, particularly for anybody moving into biochemistry, which is a significant portion of you. So, haha. Yes.
The products in black you drew, that very
Yes.
top oxygen, is that done, or would that need a negative charge?
We'd need, well, it would technically carry the negative charge, except what was step 2? Step 2 was adding HCl. What is that HCl going to do? Put the hydrogen on. Okay? Good enough? Okay. We have another oxidizing agent. This one is a little, get it, Ozer, like other, the other oxide, but it's ozone. Ozone, also a very powerful oxidizing agent. Do I have, okay. It's a little bit more selective than permanganate. If we drop permanganate in, it oxidizes. We have no way to stop, which means when we hit the aldehyde, what happens? It keeps going and it goes to the acid. But what if you want the aldehyde? Well, then permanganate's a really crappy reagent to use. You probably shouldn't use it. Okay? This is where ozone can come in handy. Okay? Ozone will react, so we take O3 and we do an addition reaction with our alkene. And you'll notice it does all sorts of crazy things. The very first step it does is exactly like the permanganate, exactly like the osmium tetroxide. There is no difference. Everything about that is identical. That next step is where it goes completely haywire. Okay? That may start to look somewhat familiar because you're sort of doing the elimination reaction that we did with the permanganate. Okay? So you might say, okay, I kind of get that. But then you start moving into step 3 with some crazy, weird arrows flying every which way. Okay? And it just looks like a mess. Ultimately, all that happens is you go all the way down to this final structure, ozonide. Depending on the textbook you use, sometimes they show you the mechanism, okay, to get to the ozonide. Sometimes they don't. Why do they not show you? What are you responsible for? So are you ready for your responsibility here? Here's your responsibility. Well, if that's all you're responsible for, why do we show any mechanistic detail? Okay. So once you're at the ozonide is still an unstable structure. Why is it unstable? Subtle hints. You have oxygen bound to oxygen. You have effectively a peroxy there. That is unstable. It is made even more unstable because we have the peroxy right next to another oxygen. So that thing wants to bust open. Okay? The way it can go through and do, or it has a couple ways that it can go through and do that. Okay? One way is to then follow this up with a second step. So this is not clear in their mechanism. This is a second step where they have added that species. Any ideas what name that compound might be? So we have methyls, yes. There's 2 of them, so we have a dimethyl sulfur. We haven't officially talked about how to name that. sulfide. Okay. The key letters out of that would be the D, the M, and the S. Very frequently, you do not see the structure, but it is written as DMS. What happened to the DMS in the course of that reaction? Where did it end up? Is it A or B? B. What changed about it? It picked up an oxygen. Okay. Well, if it picks up an oxygen, that third oxygen is not attached to our structure anymore, which means there's our aldehyde. If we instead add a different reagent that supplies more oxygens, we take it all the way to the acid. Okay. When we're dealing with our ozone, the most important sequence of reagents that you will see is the O3 followed by DMS. Why is that one more important than taking it all the way down to the acid? What did the permanganate do? It took it all the way to the acid. Okay. So if I change reagent number 2 in this reaction, I can take it to the acid, but why not just do permanganate then? Okay. There's no point in shifting to the ozone. Okay. So this is your key reaction when you're looking at ozone. Ozone followed by DMS. Does the same general idea, and you could probably come up with some mechanistic detail similar to what we just saw within the permanganates to go through and do that cleavage and get you to this aldehyde state. All right. Why do we not worry about oxidizing further in this situation? Well, DMS scavenges that last oxygen. Without that oxygen, we can't oxidize any further because there's no oxygen left. We don't have to worry about the diol forming. Why no diol? To form the diol that Cassie was asking about earlier, sorry to throw you under the bus, Cassie, how did we get that diol? We reacted it with hydroxide. Do we have hydroxide? No. Right?
So which of those hydrogens, or which of those oxygens did it take in the one in the middle?
Exact detail is not important. It's taking one of them. Yeah. And yes, there is a difference. And it's more complicated than what we're attempting to show you. So again, this is one of those just accept the simple approach.
Will it always look like stretched out like that?
You will almost always see it stretched out like that when you're running these oxidative cleavage reactions.
What's the other way?
So how we go?
Well, with the what?
Like the other way of like.
The other way would look like this. Whoops, that's the next arrow slide. Sorry. The other way to look at it would be like this. Why? Remember what we said with the oxidative cleavage. What do? Stretch the double bond, erase the middle, put in your oxygens. There it is. Okay. What I just drew is equivalent to what's drawn up, stretched out. The only reason you would see it all folded up like that, I personally, on an exam I am writing, am being nice. That is the only reason you would see it like that. I have never seen another exam where they have kept it folded up on itself, because when it's folded up, it becomes more apparent that that's what's happening. As soon as you stretch it out, everybody goes, well, how did that happen? Right? Other questions? And in the case of the ozone, you leave the hydrogen when? When do you leave the hydrogen? Why does it stay in aldehyde? Why is there no more oxygen? Because you have DMS. If you don't see the DMS, you're going to have to put in the oxygen, which gets us to, very next slide, what happens now? When we look at the reagents, you start with ozone. Step 2, what have we supplied? Peroxide. Ultimately, we supplied a bunch of extra oxygen. What's the end result? There's a reason there's a giant box there. You go all the way down to the acid. Okay? Questions? So, ozone is an oxidative cleavage reagent. There are two workups to go with ozone. One of them is a reductive workup, which doesn't make any sense because it's still an oxidation reaction. Okay? But it's a shorter oxidation reaction or a less oxidative reaction. And then there's the oxidative workup, which gives you even more oxygens. You just push all the way to the fully oxidated state. Okay? Questions? Okay. That is all of 24, including the Diels-ALder stuff. That's why there were lecture videos on the Diels-ALder. We talked about it a few times in class, getting you through problems. Watch those videos, work problems with Diels-ALder. Okay? This was the rest of it. Okay. Theoretically, and this is potentially fun, we talked about ozone, permanganate, and osmium tetroxide. When did you first see those? Think back, when did I first see that? When did you see them show up in an addition reaction? In that big chart, which showed up for you guys, for the people that had me already, first semester. We haven't even started talking about second semester material. Okay? Questions? Oh, God. I always forget about this. Nomenclature. This one slide pretty much has everything that I think you could possibly need with nomenclature as far as the basics go. Right? Chapter Nomenclature 4 in the Carty textbook will go into a little bit more detail. You'll notice they bring in more functional groups, like the cyano group. Okay? You'll have to incorporate those into the priority lists and understand how to go through and name them. Why do I not include them in my table? Why do you not see the nitrile, carbon triple bond nitrogen? You don't have to name it very often. Okay? There's a lot of things that are missing from this that are involved in nomenclature that you don't necessarily need because they don't show up quite as frequently. What I try to do is condense this down to the bulk functional groups. These are the major functional groups. There are plenty of others. Okay? As Will talked to me about earlier, we had imines. Anybody see imine on this list? Nope. We just talked about acetals. Do you see acetals on this list? Nope. Okay. We've got amides. So we've got these other functional groups. You need to know what these names are, okay, and roughly how to name them. That's what this slide will help you with. Okay. After that, we've got all sorts of extra rules that come in when we introduce aspects of stereochemistry. You have alkenes. An alkene could potentially be cis or trans. If we change the arrangement of the groups around the alkene, does that change its physical properties? Yes. That is why we have saturated fats and unsaturated fats. We get drastically different properties out of those two materials. All that is changed is we took the fat from having, well, actually it's not even saturated and unsaturated, but we could have trans fatty acids and cis fatty acids. That subtle change in cis versus trans changes the fatty acid from acting one way to an entirely different fashion, biochemistry. So being able to name and recognize those, you need to have a rule set. R and S, you're looking at stereocenters. How do you know you have a stereocenter? There are 4 different things attached to an atom. Does it have to be carbon? No. It can be any atom. Okay, so you could have nitrogen, you could have phosphorus, you could have sulfur. 4 different things through sp3 hybridized bond, or through sigma bonds. Okay? Why do we not care about all those other ones? What?
We don't see them very often.
Why do we not see them very often in this class? Because this is organic chemistry and we look at carbon. Okay? Both R and S and E and Z, or cis and trans, come back to the same set of rules, the Cahn-Ingold Prelog rules, which is assigning priorities based on atomic mass. Okay? And I'm going to trust that I actually wrote that down right. So it's the atom attached, not the group, the atom attached. You can have a massive group connected to a carbon, but a lowly OH will win out. Why? Oxygen has a higher atomic mass than carbon. I don't care what happens after those atoms. It's where that initial difference happens. It's an atomic relationship. Once you've assigned priorities, you can then go through and evaluate either Z and E if you have an alkene, or R and S if it's chiral. Okay? You have to follow the rule sets. If you don't follow the rule sets, you will get the wrong answer. Okay, pieces of a name. We've got location, you've got amounts of a substituent, you've got what the substituent is. That can be repeated indefinitely. Well, not indefinitely, but multiple times to account for multiple different substituents. Okay? The location numbering may need to be repeated, or has to be repeated, for every substituent. So if you have a dimethyl, you have to tell me where both methyls are. Okay? So that would be location 3 and location 4. You have to provide those. Shape kind of comes in, sort of. There's only one shape you need to remember. Cyclo. Okay? If it's a ring, show cyclo. If it's not a ring, it's not cyclic. Okay? And I kind of feel bad about pointing this out. First semester, the ACS exam, there were a lot of cyclo versus not cyclo answers in the naming on the final exam, and people getting them wrong. Cyclo means ring. Not cyclo, don't draw it as a ring. Okay? After that, the number of carbons, okay, specified in English. So we've got meth, meaning 1 carbon, eth, prop, bute, hex, pent, non, 9. Good. Yeah, I was attempting to. Carbon hybridization also gets specified. What do we mean by carbon hybridization? If your carbon is all sp3, how do we specify that all of our carbons are sp3 in the name? It's an alkane. They're anes. Okay? What if we have a double bond in there? And the carbon just became sp2, which means it's an ene. Okay? So the hybridization of our carbon is implied in the name. The last part is the location and name of our primary functional group, the one of the highest priority. Okay. Let's spend 2 minutes cranking out these names, because I've got it drawn.
If you rotate it.
There we go. Realize when you're dealing with nomenclature, it's not going to particularly going name to structure. You will probably draw it left to right. Guess what the answer choice will show? Almost always right to left. Okay, why? It's, again, messing with your head. Same deal as the Diels ALder. You have to remember these structures can spin, flip, and rotate. Okay? For either of these structures, should extra information have potentially been supplied in the name? I know, that was kind of a hard question. For any of these answers, is it possible, or should we have supplied more information in the name?
In the cyclohexane, you could have whatever.
So MP and O is an interesting dimension. That only applies to benzene. Do we have a benzene? No. We have to consider stereochemistry in the third example. At what position? Position 2, the one with the OH. Is that it? You also potentially have stereochemistry popping up in that cyclo compound, which we could dodge by calling it cis or trans. Okay? So be aware, sometimes you need to supply it, sometimes you don't. If you don't need to supply it, don't worry about it. Okay? If you see R and S or E and Z show up, worry about it. Okay? Questions? Actually, new question. When should you worry about R and S, E and Z? What? But when you see a question, there's one option. Let's say this says, there's your new name. When do you worry about R and S? Say, draw the structure. When do you worry about R and S? After you have the skeleton drawn. Get the skeleton correct. Don't worry about the hard stuff until you get the easy stuff. Okay? Because it could very well come down to they may be asking for RNS, or I may ask for RNS, but only one answer has the correct skeleton. In which case, do you need to worry about RNS? No. Okay? So don't panic if you see stuff that's foreign to you. Get the easiest stuff down first. Okay? Advanced naming, go ahead and give these three a shot. Give you a little bit more time. People are already challenging the hept. Drop in there. Hept is absolutely the longest chain. Okay? Remember, it's the longest chain including the highest priority functional group. The aldehyde is the higher priority functional group. That is 7 carbons. Yes, I may have an extra carbon out here, but that does not include the longest chain, or the primary, or the highest priority functional groups.
So aldehyde's always higher than
Yep.
alcohol?
Yep. So that ends up getting referred to as a propyl. We have an alkene floating through the middle there. In fact, actually, I'm going to erase that for a moment. That alkene is located at position 1, 2, 3, 4, isn't it? Should be 4. Ene. We name our aldehydes by saying al. Our propyl is at position 3. And then we have the alcohol at 7. I should have known that. 7. And how do we say alcohol? All only works if it's the end. It's not the end of the name. Okay? So it ends up getting referred to as 7-hydroxy, 3-propyl, hept 4-ene, al. Why did I not specify the location of the aldehyde? By definition, your aldehyde will always be at the beginning or end of the chain. If it was a dial, then I might specify the names or where they're located. But since there's only one, it has to be at the beginning of the chain. Mm-hmm. But remember the hybridization classification? The hybridization classification comes in the parent name, if you want to call it that. It's not considered a substituent. Okay. And then I think I got the order right there. It will go 7-hydroxy, 3-propyl, hept, 4-ene, al. We would not go 3-propyl, 7-hydroxy because our substituents go in according to alphabetical order. Okay, so H comes before P. The next one, it says hexanal. Aldehydes are our higher priority group, but we also have a carbonyl. It's a little bit more than that. It's a ketone. How do we specify a ketone when it's not the primary functional group? Oxo. Okay, and it shows up at 1, 2, 3, 4. We got 4-oxo hexanal. How do we know that? Well, it would be nice if somebody had provided a summary that actually says how to name it when it's not the parent, hence the parentheses. Okay? So that's why I think this slide is incredibly useful. Whenever anybody asks me nomenclature, I go back to my own slide to reference it. Mainly because, for those of you that haven't met me before, I am horrible at nomenclature. I absolutely despise it and think it is a completely meaningless, useless thing to memorize. Okay? That said, I accepted that point loss. And I lived with the grade I got. Okay? Your choice if you want to ignore it. Okay. Whoops. Whoop. Last one, let's see if I can do that last one real quickly just because I put it on there. 2, 4, 6, acid, 2, 3, 4. We have our 6-hydroxy-4-oxo-hex-2-ene-oic acid. In theory, I put that together right. Okay. Questions? Okay. So far this semester in 2 weeks, I'm on a record because we've now covered 1, 2, 3, 4 chapters. You're like, no, we haven't. Yeah, we did. Chapter 11 was your acid addition to alkenes. It was review, but we talked about it. Chapter 12 was looking at standard addition reactions with your electrophiles, bromine, mercury, all that fun stuff. Chapter 24 was Diels, ALder, and all the oxidation reactions. Nomenclature 4, we just did. Okay? I will try to keep throwing nomenclature at you guys as examples. Hopefully I can do it every week, primarily because it looks like you guys are taking on the sins of the instructor, and your nomenclature is pretty weak. Okay? So I'm going to try and throw more nomenclature at you to make sure you get those questions on the exam. Okay? Questions? Now, in the next 2 minutes, we're going to do a quick review, and then we'll talk about what the rest of the plan is for the rest of up to exam 1. So, substitution and elimination reactions. This was a major part of first semester chemistry. We've got the general reaction shown for our substitution, and I should have shown the one for elimination, but I forgot. They both break down into 4 main components. Substrate, your leaving group, the nucleophile or base, and solvent. Every time you look at a reaction that you are trying to decide what type of reaction it is, look for those 4 things first, because that may help you decide substitution or elimination as opposed to addition and all the others. The next part of it is depending on the characteristics of the substrate, that is going to push different mechanisms. Why are the mechanisms relevant? It's going to change the stereochemistry of the product that you end up getting out of it. Okay? So on a multiple choice exam, you don't have to draw curved arrows, but you do need to know exactly where all the groups go. And you either memorize a ridiculous amount of information, or you understand something about how the reaction works. Okay? So those are your 4 basic elements. When we look at our mechanisms between SN1 and SN2, this is a nice little summary that I've used, and it's helped me a lot on trying to decide which mechanism I run. So we look at the substrate, you look at the nucleophile, you look at the leaving group, and you look at the solvent. Depending on that information, that will help you decide, am I doing SN1 or am I doing SN2? Once you know which one to look at, you can then say something about the stereochemistry. Okay? And you can now predict what's happening with the product. Same idea with the elimination. Okay? Those of you looking at the PowerPoint slides, you will notice that these are not immediately in the most recent show. It is in the review slides posted earlier. I looked at what I'd put together and I didn't have enough of a review on substitution and elimination. I wanted to make sure everybody had access to this information. So the review slides posted at the very beginning that we haven't talked about at all do have these slides in them. Okay. Next part about it, your textbook has come up with this idea of predicting the outcome of your substitution and elimination reactions. So looking at different mechanisms. They came up with this table. I have no idea what this table means. I've read the book, I've looked at their chapters, I've looked at the table, it confuses the hell out of me. I don't know what it's trying to get at. I can fudge it, but it's confusing to me. So instead, I use a different kind of modified thing. And because they did a nice table, I decided to modify mine so we have a table. Look at the substrate. Okay? What mechanism supports that substrate? How do you know what substrate? Well, that means going back and looking at your mechanisms, okay? And evaluating through that middle part for our substitution what our individual results come out to be. Okay? So you can look at the substrate and say, okay, what am I going to get? Okay? Then you can look at the strength of the nucleophile. Okay? If it's a strong nucleophile, that favors SN2. If it's a weak nucleophile, it favors SN1. So we can put a check in either of those boxes depending on what you're looking at. You'll notice under the strong nucleophile that I have grayed out E1 and E2. Why? Those aren't relevant because in E1 and E2, I don't want a nucleophile. I want a base. Hence the next line, strength of the base. Then look at the leaving group, then look at the solvent. I will admit leaving group is a pretty meaningless category because what does an SN1 reaction need? Leaving group, what is an SN2? E1, E2. It's a pretty useless column or row. Okay? You need a leaving group. If you don't check the leaving group category, you're answering the wrong question. Okay? Because you're now looking at the wrong reaction. Go through, look at your totals. Whichever one has the highest total of checks, that's the mechanism you should be running. Okay? Which means go back if you haven't got them memorized already and look at the results that comes out of it when we're looking at stereochemistry. Okay? So I'm going to stop recording now because what we're going to talk about